attached.
Right.
And in writing it out this way, this one compared to these three, same thing. These are the three that are firmly attached.
Okay.
That's the one that's loose.
Okay.
Okay. But now that's something that comes out of Lewis structures. Don't anybody write this down. Okay, you can just ignore this or file it under trivia. But this is the Lewis structure for acetic acid. These three hydrogens are bonded to carbon, and hydrogen to carbon bonds are pretty much nonpolar. That's perfectly equal sharing. These three are very firmly attached to the carbon. But this one doesn't have a carbon, it has an oxygen. And oxygen with high electronegativity makes this bond extremely polar. Remember hydrogen bonding forces. That bond is extremely polar, and so it doesn't take much of a nudge energetically to pop that hydrogen free. It's not getting much access to the electrons anyway, all right? And so that's why it's written that way, because that comes out of organic chemistry, where they show you each carbon and what's on that carbon. So the first carbon has 3 hydrogens, the next one has 2 oxygens and a hydrogen. That's where you get that CH3COOH notation, right? But without going any deeper into structures and stuff like that, COOH is a dead giveaway, it's an acid. Now I'm going to put one of these reactions back up. You don't need to recopy this because it's already on your page. But you may want to label it as we go through here. And actually I'm going to color code it a little bit. With this ionization, HC2H3O2, that is an acid molecule. And so the hydrogen leaves there and goes to the water. Now when we did the definition for ionization, I said it was transfer of a single hydrogen, then parenthetically from acid to base. Which in that sense, that's saying that water is base. In this case, it's behaving like water. Over there, we got, as our first definition of base, a material that produces hydroxide ions in solution. A second and more broad definition of base is acids create H+ and bases counteract it. Hydroxide is significant because hydroxide is good at counteracting H+, but it's not the only thing that can counteract H+. And so other things that can do the same job get considered bases as well, even if they don't look like your traditional base. If the hydrogen goes from here to here, then this is releasing H+ into solution, and this is latching onto that H+ and bonding it out of solution. And that gives you these products. But now the reason I've color-coded this, if you think about the reverse reaction here, when these two revert back to original form, then this hydrogen's going back where it came from, correct? Which means this hydronium is behaving as acid, and this acetate ion is behaving as base. that makes it look even worse because that doesn't look like your typical base either. But it's doing the job of counteracting hydrogen. From and to. When you're dealing with ionization, you trace the hydrogen where it goes from and where it goes to. It goes from the acid and to the one you consider the base. And that gets us to this idea of what's called conjugate acid-base pairs. Acetic acid in the forward reaction forms acetate, and acetate in the reverse reaction forms acetic acid. And so if you've got a beaker of water there, and you put in perfectly pure acetic acid, it's going to react to form acetate ions. Or if you took perfectly pure acetate ions and put them in water, it would react to form acetic acid. They're called a pair because in solution it's impossible to have one and not the other. In solution they always coexist. And I'm not saying they're equal proportions, but that's just what acetic acid does. It transfers the hydrogen and forms acetate. Acetate gains hydrogen and that forms acetic acid. And those would be going continually in the solution. So these are inherently linked by that transfer of a hydrogen. One form has it, the other form doesn't. The acid form has the extra H+, the base form does not. And there's an inverse relationship of strength. The stronger, let's put this one back. Acid, base, acid, base. Comparing acetic acid and hydrochloric acid, which one is the stronger acid? Hydrochloric, because it's on your strong acid list, correct? This is strong, that's not. That's reflected in the arrow whether the hydrochloric goes to completion, which means there is no reverse reaction. What does that tell you about the chloride ion's strength as a base? Zero strength, right? So the stronger the acid form, the weaker the base form. So when you're looking at an acid-base pair like that, that's the inverse relationship. It's not so much acid and base, it's acid versus base, if you want to think of it that way. The stronger the acid form, the weaker the base form. The stronger the push in the forward direction, the weaker the push in the reverse. If that reaction is 100% in the forward direction, that means the reverse is 0, correct? And why we don't even bother to write it. So that chloride ion really is just a base in name only, because it's not going to gain the hydrogen, it's not going to function like one. But it fits in that inverse pattern of strengths. Technically, the chloride ion would be considered the conjugate base of HCl. And in these acid-base pairs, they're always just a single hydrogen different. And so if you're trying to predict the formulas for an acid-base pair, you don't even need to write the reaction, really. If this is an acid, what would be its conjugate base? NO3 negative. You take the H plus away. HNO3, if it loses the H plus, what's left? NO3 negative, and that's the base form. It'll be a single H plus difference. The acid form has the H plus, the base form does not. What if the acid was HCl3 minus? What if this is functioning as a base? What would be the acid corresponding to that? an H plus back onto it. If that's the base form, you want the acid form. It'll be a single hydrogen different. What's it going to be? It's going to be a single hydrogen different. The acid form has one more H plus than the base form. And there is no other structural difference. Now, polyprotic, poly just meaning several, these are acids that have multiple acidic hydrogens. Not multiple hydrogens, but multiple acidic hydrogens. Remember, we had this one a while ago that had multiple hydrogens, but how many of those 4 hydrogens were actually acidic? 1, and that's why we had just a typical reaction was just 1 step. If you've got ones with multiple acidic hydrogens, this is when you get a series of reactions. Carbonic acid reacting with water. It's an acid, so it produces hydronium. It's transfer of a single H plus, so it loses one of its hydrogens. Like what we did here. So HCO3 negative is your product. A hydrogen goes from the acid to the water. Those are your products. Is carbonic strong or weak? Weak, therefore two-way arrow. Question about that? We're not done yet because that product, HCO3 negative, still has an acidic hydrogen. And that means there's going to be another step to the ionization. That particle could react with another water molecule to make another hydronium by losing another H plus. And if that happens, what's left this time? You'd have no hydrogens left, so it'd be CO3. And what's its charge this time? Good. 2 nice. For each hydrogen you strip away, it becomes progressively more negative. That would be balanced chemical equation for ionization of carbonic acid. Question about that? Now, before we go any further, let's pause right here for a second. Have you noticed that we've not been having to balance these ionizations? If you key in on the transfer of a single hydrogen, then everything is going to work out fine. By definition, ionization is going to always have coefficients of 1. There's not going to be any balancing to do. As long as you're careful about pulling the hydrogen from here and putting it there, then nothing else changes structure. And they will always be self-balancing this way. Question about that for carbonic acid. It has 2 acidic hydrogens, therefore it's a 2-step process. That's both steps. All right. Do phosphoric acid. unless you're specifically asked to. If you're just asked to write the ionization, then you don't need these labels. This is the first step. Is that what you got for the first step? Yeah. And this should be the whole process. You've got 3 acidic hydrogens, therefore it's a 3-step process. You're just plucking off those hydrogens one at a time. And so by the time you get done, you're down to plain old phosphate as your last ion, which will be a -3 charge. Question about that?
Phosphate always have a -3 charge.
Phosphate?
Yeah.
It does. But now even if you forget that, what you're working with initially should tell you what its charge is. Because if these hydrogens are +1Es, then that has to be a -3. So even if it's an ion you don't recognize, you can figure out its charge based on how many hydrogens it has initially. All right, question about writing that for phosphoric acid. All right, multiple step process. And let's go back and look at conjugate acid-base pair definitions. On the carbonic one, H2CO3 was acid, HCO3 negative was base. Because in that first reaction, it could gain hydrogen back, and that would be the reverse process, correct? But there's also something a little different with this one, in that this HCO3 negative that could regain that first hydrogen it lost, it has another option for reacting too. This particle is that particle, right? It was formed in the first step, and it's going to do one of 2 things. It's either going to revert back where it came from, and that would be base behavior, or it's going to go ahead and get rid of its other hydrogen, and that would be acid behavior. And that would form carbonate. So as far as acid-base pairs go, carbonic acid and HCO3 negative, that's an acid-base pair. HCO3 negative and carbonate, that's another acid-base pair. But the peculiar thing here is this HCO3 negative ion has both abilities, correct? And when you've got something that has both abilities, that's called amphoteric. Amphoteric is different from acid-base pairs because acid-base pairs is a pair. It's 2 formulas, one of them being acid and the other being base. But amphoteric is a single substance that inherently has both abilities. HCO3 negative is amphoteric because as that single formula, it has both the ability to lose hydrogen and gain hydrogen. Go ahead.
You answered the question.
Oh, okay. All right. Here's your key structural characteristics. To be amphoteric, it has to have hydrogen that it can lose, and it needs to have a negative charge that could lure a hydrogen in. The negative charge gives it the ability to gain hydrogen. The acidic hydrogen gives it the ability to lose hydrogen. Amphoteric is a single formula with both abilities. generic formula would be something like this. Where X just represents anything, monatomic or polyatomic. Something that has structurally an acidic hydrogen and a negative charge will inherently have both functions and therefore will be amphoteric. The exception to this pattern is water. Even though water doesn't have a negative charge, it does have the ability to gain hydrogen and lose hydrogen. So water is amphoteric, even though it doesn't look like it. And this HX minus category is amphoteric. Water is the only neutral substance that's amphoteric. Question about that? All right. Is this amphoteric? No. Is this amphoteric? No. Is this amphoteric? Yes. Is this amphoteric? Do you know what compound that is? Then how do you know it's amphoteric?
Because it has a negative hydrogen and negative charge.
Acidic hydrogen and negative charge. That's the structural things that matter, right? Now careful on this one. Is this amphoteric?
No.
Why not?
So it started on hydrogen.
It has to start.
Don't fall for it.
It needs to start. It needs to have. It doesn't have a hydrogen.
It doesn't have acidic hydrogens, right? Having hydrogen is not what matters. It's having acidic hydrogens. And not having those out front is telling you that that has no acid ability. Okay? So be careful with that. It's having acidic hydrogens that matters.
I got it. Isn't the first one and the third one the same because we moved the hydrogen?
It's the same ion in here, but this would be essentially a base form. This would be an acid
Oh no, I'm
form.
talking about the first one and the third one.
This one?
Because we're gonna move the hydrogen to the negative. It's gonna be 3.
I'm not going to write this out like what we did there. I'm going to shorten this a lot, but this would ionize and form this. This would ionize in another step and form this, and this would ionize in another step and form this.
Yeah.
Okay, very much like the phosphoric or the carbonic over there, where you pull off the hydrogens one at a time and it gets increasingly more negative, right? This is an acid because it has the ability to lose. This would be considered a base because it has the ability to gain. And both of these that are in between have both. And so both of these are amphoteric.
So would that be the same case with the H2PO4 minus and then the H?
Yeah, exactly. These ions are amphoteric. That's right. Other question? Number 13. Balanced chemical equation for ionization of HF. We had this up a while ago, putting it in here for comparison. HF is an acid, so it reacts to form hydronium. The remnant would be fluoride, and because it's weak, it would be 2Y. NH3 is ammonia. Not ammonium, but ammonia. And it's neutral, and the hydrogens are not written at the front. That's telling you it's not an acid. Ammonia is a weak base. Weak meaning the reaction we're going to write is going to be 2 A atoms. And base meaning it gains hydrogen, not releases. It gains hydrogen from where? Apparently water, because that's your only other reactant. Ionization is always somebody plus water. And so what's happening is the hydrogen is going from the water is considered acid, to the ammonia, which would be considered your base. NH3 would become NH4 positive, and the remnant from the water would be hydroxide. The water gets converted into hydroxide.
You're adding hydrogen.
The ammonia is adding a hydrogen from the water, yes. Remember, the hydrogen always goes from the acid molecule to the base molecule. So in this case, the hydrogen is going to the ammonia. Go ahead.
Is there a list of weak bases?
Everything that's not strong. Yeah, and ammonia is really the only one you need to memorize as far as on site, okay? Because things like that, there's a lot of them, and you'll deal with a handful of them in Chem 2 if you take Chem 2. But for our purposes, for now, it's just going to be ammonia. It creates hydroxide. That's why it's considered a base. That's back to our first definition of a base, right? Things that create hydroxide as independent particles are considered bases. Ammonia does not look like your typical base, because your typical bases were metal hydroxide compounds, and this is not. But it still gets the job done. It still makes hydroxide. Therefore, it's still considered base.
So if it says that ionization, that means we're gonna add, it's gonna be plus water, and then we just have to know whether or not it's acid or base to know whether we're gonna add a hydrogen or subtract hydrogen.
Yeah. And you know how to recognize acids notation-wise, and so if it's not an acid, then by default it has to be a base ionization. It's the only other kind.
What if it was a strong base instead of a weak base? Would that change things?
If it were a strong base, then you'd be doing dissociation, not ionization, because all your strong bases were metal hydroxide ionic. You're not going to have any strong base ionizations. In comparing these two reactions, look where the hydrogen is going from and to. From HF to the water, water behaves as base. From the water to the ammonia, water behaves as acid. There's your example of water being amphoteric. If you've got a beaker of perfectly pure water, then that water is neutral. But if you put in acid, water behaves as base. Or if you put in base, water behaves as acid. It can do either one depending upon the situation, even though it's neutral. Do you see that water has both abilities? All right, then do number 14. It's not a trick question. Granted, it looks funny, but it's really not different than what we've done on the previous ones. One of them is going to release hydrogen, and the other gains it. The one that gains becomes hydronium. The one that loses becomes hydroxide. One of these waters, depending upon, if you think about the beaker of water and the molecules tumbling around randomly, every now and then they're going to collide at just the right angle and just the right energy for a hydrogen to transfer over. It's going to happen. One of these then is functioning as acid, the other is functioning as base. But water, whether it's acid or base, is never strong. And so this is going to be two-way arrows. Is this what you got? All right. Put a big star by this one. If you're going to be taking Chem 2, then cross that out and put an even bigger star by it. Biggest star you've ever made in your life. It's that important. Because that reaction is the foundation of the pH system. And you'll deal a lot with that when you get to Chem 2. It's important now. It's even more important if you take Chem 2. Right? It's the foundation for an awful lot of things. So, be aware. Question about that? All right, we did not get to neutralization, but that's okay. So we've covered these two. On Wednesday, you'll be going over neutralization. That's the last of the reaction types. The pages you've got left here as far as reactions go. You've got neutralization, net ionic equations, electrolytes, those kinds of things will be done on Wednesday as well, all right? So we'll do the last